Hello and welcome to today's video. Today's video is for Advanced Geometry Chapter 12, Section 4, Angle Measures and Segment Lengths. So we start out with a definition of a secant. A secant is a line that intersects a circle at 2 points. So if I draw a circle and then I put a line through it that intersects in 2 points, that's called a secant. If it intersects in one point, it would be a tangent. And if you take a look at a secant, the part within the circle from endpoint to endpoint is called a chord, and then the whole thing is a secant. Okay? So we have a theorem that says that the measure of an angle formed by two lines that intersect inside a circle is half the sum of the measures of the intercepted arc. And if they intersect outside the circle, it's half of the difference of the intercepted arc. So for the first example, I have two secants that intersect inside. So what this one is saying is it's saying that the measure of angle 1 is half the sum of the measure of arcs x and y. And you can also say the measure of, I put a little 2 here, the measure of angle 2 is also 1/2 of the sum of the arcs x plus y, since they are since they're vertical angles, so they're both the same. And then in the second example, we have the secant and in tangents. We have them outside, and for both of these examples where the lines intersect outside the circle, then the measure of the angle is 1/2 the measure of the larger arc minus the smaller arc. So this works if we have two tangents, so this works if we have two secants, like the first example, if we have a tangent and a secant, like the second example, or if we have two tangents, it still works. So remember that all the way around the circle is 360, so you could actually write this last example, since x and y cover the whole circle, you could also write that the measure of angle 1 equals x minus 360 minus x, because that's what y equals anyways. So we are going to prove this one for the inside, the two meeting inside. And notice for the proof, we actually are going to draw an extra line in there to help us. So we're going to prove that if we have a circle with intersecting chords AC and BD, so two secants that intersect inside the circle, then the measure of angle 1 equals 1/2 the measure of arc AB plus the measure of arc CD. So here we have some quick examples. So for the first one, they intersect inside, so x equals 1/2 the sum of the two. So I'm going to take half before I'm going to distribute it. And for the second one, the angle, which is 20 degrees, is 1/2 of the difference between the larger arc measure and the smaller one. So 20 equals 1/2 of 95 minus z. So I'm going to multiply both sides by 2. So 40 equals 95 minus z. And if I subtract, I get negative 55 equals negative z. So z equals 55 degrees. Now this next one deals with basically their proportions, but it's got 3 different examples. Okay, so these deal with the length of segments that are within these secant lines or chords or tangents. So this one says, for a given point and a circle, the product of the lengths of the two segments from the point to the circle is constant along any line through the point and the circle. So what this one is saying is that if I start out with a circle and then I put a point anywhere, either inside or outside, so I'll first put it outside, I can draw various lines that'll intersect a circle. Maybe they intersect once, maybe they intersect twice. So I can draw one that, like here, that intersects twice. And I could draw one that intersects here, which only intersected once because it's a tangent. And what they're saying is if I take the lengths from that point to the two places it crosses the circle, or if it's tangent, the place where it crosses the circle twice, you do it twice, then the product of those are constant. So if I call this x, and I call this y, and then this from the second point all the way back, I call this z, then what they're saying is the product of the two lengths along the one line, so yz, is the same as any other line that I would draw. And if it's tangent, you just do the length twice. And essentially what you're saying is it intersects twice, it's just the same point. So equals x squared. Now the one inside is easy, because if you look at this example, from the point to the one intersection, it goes this way, and from the point to the other place it crosses, it goes this way. So you don't have to, they don't overlap at all. And if you take the one direction for the second one, it goes this way, and the other way, it goes this way, and those don't overlap either. So for this one, it's A times B equals C times D. Now the second one has some overlap because you actually have to go through the first intersection point to get to the second one. So this one is saying that if I go to the point of intersection for the first time, I get W. But if I go to the intersection point for the second point, I have to go through W and through X, so W plus X. That's going to be the same as if I go this line and I go first to the first point of intersection, which is Y, and then I go through Y and through Z to get to the second one, which is, so this one is X plus W and this one is Y plus Z. So for the second one, you see you do have some overlap because to get to the second intersection point, you actually have to go through the first. So if I take W times W plus X, that equals Y times Y plus Z. And the third one deals with, well, what happens if one of these points is still outside? One of them has two intersection points, but the other one only has one. So for this one, the first part kind of looks the same. There's to the first one, and then we have to go through the first one to get to the second one. So it'll be Y and Y plus Z. But for the tangent one, what we do is we just count this as being an intersection twice. So we do T, and then we do T again. And so notice it's T squared. Okay. So basically it's the same rule, it's just whether it's inside, outside, or whether the intersection it occurs twice, or whether it's tangent and it only occurs once. Okay. So we are going to prove this one, and again notice we have some pictures drawn. Those pictures are very suggestive of having to use the inscribed angle theorem, which we will. So we want to prove that A times B equals C times D. We will use similar triangles to do this, a little similar triangles and cross multiplying. And then we have, after that, a couple examples and then a nice little problem. Okay, so find the value of the variable. So for this one, this is where we have the intersection twice and it's outside. So according to this one, if we go from the point of intersection to the first place it crosses the circle times the intersection point to the second place it crosses the circle, which is 6 plus 8, that should be equal to, whether we do it this way, we go to the first intersection point and then we go to the second one, in which case we have to go 7 and then Y more. And then we can, so 6 times 14 equals 49 plus 7y. I'm going to divide by 7 so I don't have to multiply. So this would be 6 times 2 equals 7 plus y. So 12 equals 7 plus y, subtract 7, and y equals 5. So this is 5. And we can do a little check. Is it true that 6 times 14 is the same as 7 times 12? So this one is 84, and this one is also 84, so check. Okay. And the second one is that tangent one. So if we go from the point of intersection to the first crossing, and then the point of intersection to the second one, double check that you add those together. That's going to be equal to, and then for this one, z, and then z again. So z squared. So this is going to be 8 times 24 equals z squared. So instead of multiplying this out and figuring out what I've got, what I have to do is, I notice that I have a factor of 8 twice because 8 is in 24. So what I'm going to do is I'm going to make it 8 squared times 3, and then I can bring the 8 out. So z equals 8 root 3. Quicker than multiplying it out than figuring out what's in there. And then the last example, we have this arch. It's called the Takabashi Bridge, I believe. I might be saying it wrong, sorry. Is an arc of a circle. A 14-foot chord is 4.8 feet from the edge of the circle. Find the radius of the circle. So the bridge is only at the very top of this arc. So the rest of it would go down into the ground. So it's a 14-foot chord. And it's 4.8 feet from the edge of the circle. So what I know about this is I can, if it's right at the very top, then it's going to bisect this, so that's going to be 7 and 7. And then if I extend this all the way down, I get an intersection of two chords that are inside. So what I'm going to do is I'm going to call this x. And so what I know is if I go 4.8 and I multiply it by x, that's going to be the same as in the other direction, which is 7 times 7. So 4.8x equals 49. And if I divide by 4.8, I get 10.2. I'll call it 10.21. So this is 10.21. So, and I've got that other part that's 4.8. So if I take 10.21 plus 4.8 and divide by 2, that's going to be my radius. So plus 4.8 divided by 2. And I get that it's about 7.5. So about 7.5 feet. And that's it for today's notes. Thank you for watching.